Hello and welcome back. We have been studying the conditions of static equilibrium. Today we'll develop the concepts further. But before we do that, please take a moment to hit the subscribe button and join us in this wonderful journey of learning structural engineering with STAT. Now, let us consider this ball in space and it's subjected to a system of general forces. Now, there can be any number of forces on the ball, but to represent it with simplicity, we have only taken three forces to represent the general system of forces. Now, each of these forces has three components in space. Now, for now, we have been only talking about the force in x and y axis, but now if the force is in space, this can also have the component in the z direction. So, let us consider this force F1, which has a component F1x as the component in the x direction, F1y is the component in the y direction, and F1z is the component in the z direction. For the force F2, let the component x be F2x and the component y be F2y and the component z be F2z. Similarly for F3, we write the components in the x direction as F3x, the component in the y direction as F3y, and the component of the z direction as F3z. Now, so basically then, there is a resultant force, the summation of the force in the x direction would be given by F1x plus F2x plus F3. Similarly, the summation of the force in the y direction would be given as F1y plus F2y plus F3y. And the summation of the force in the z direction would be given as F1z plus F2z plus F3z. Now, these are the resultant forces in the x direction, y direction and z direction. For this ball to remain in its equilibrium position, this summation has to be 0. So, if the ball does not need to have any translational motion in space, then it's very important to ensure these three conditions, fx equal to 0, fy summation of fy equal to 0 and summation fz equal to 0 are satisfied. Note that if there is a net force along any of the direction x, y and z, the ball will not be in equilibrium and there would be a corresponding movement of the ball in that direction. Now you may remember that forces would only cause the ball to move translationally. But if you remember, there were three rotational degrees of freedom and the ball would rotate in those directions if it were acted upon by respective moments in those directions. Note that we have been representing the force in its vector notation like this. This means that the length of this vector represents the magnitude of the force and the arrow mark represents the direction in which the force is acting. Now, to cause rotations, the ball needs to be subjected to moments. The moments can be represented in these vector notations with double arrows, like this. So, basically, the length again here would represent the magnitude of the moment, while the double arrows signifies that it's a moment, not a force, and the direction of that moment is, if you point your thumb towards the direction of the arrow, then the direction of the finger would give you the direction of the moment. So basically, this moment would be represented as like this. So it would be anti-clockwise, it will be applied in anti-clockwise manner about the axis. Now, we won't go in details in this, but it's an important part that to be in complete equilibrium, the ball does not need to undergo translation or rotation. So, like the three conditions to avoid translational motion, there are three conditions to avoid the rotational motion. What are they? It would be the summation of mx, which is the summation of moments about x-axis should be 0. The summation of the moment about the y-axis should be 0, and the summation of moments about the z-axis should be 0. Note that the vector addition or subtraction of moments is exactly similar, or it follows the same rules as the vector addition subtraction of a force. So that isn't different. So like the three conditions of equilibrium of a ball against translation, there are three conditions of equilibrium for a ball to be in equilibrium against rotational motion. So if the net moment were not 0 about any of the axes, the ball would start rotating about that axis. So for the ball to be in static equilibrium in space, 6 conditions of equilibrium needs to be satisfied. The 6 conditions are summation of fx equal to 0, summation of fy equal to 0, summation of fz equal to 0, summation of mx equal to 0, summation of my equal to 0, and summation of mz equal to 0. So these 6 conditions has to be satisfied for the ball to be in the condition of static equilibrium in space. These are the 6 conditions of equilibrium. It's interesting to note that the whole branch of structural engineering is dedicated to achieve these 6 conditions of equilibrium with maximum efficiency and minimum cost. You will appreciate this more as you continue your journey as a structural engineer. I hope you have liked this video. If you have, please press the like button and please hit the bell icon for more notifications from this channel. If you have a question, please ask in the comment sections below. I hope to see you in the next video. Thank you and bye bye.